today's discussion, we begin the study of thermal physics. By thermal physics, we mean transformations of heat energy between systems and the accompanying changes in temperature, which may occur, or work that the system may do, or changes in the internal energy of the constituents of the system. Oftentimes we'll be referring to a gas, and therefore in the process of going through this examination of thermophysics, we will begin by looking at temperature scales, looking at the effects of temperature being added to different phases of matter, solid, liquid, and gas, see what kind of response the phases have to that addition or removal of heat energy. We will be looking at some assorted properties that occur when heat energy or temperature increases or decreases are subjected to a system, such as thermal expansion, conduction, convection, radiation of heat energy, heat transfer methods. We'll then move into the area of material properties that relate to the addition or deletion of heat energy. How does a material respond to heat energy, and what can we determine about that material by measuring its response? And then finally we will conclude with the important area of thermodynamics, which is the area in which we begin to look at the cause and effect relationship between heat energy and the system that the heat energy is being involved with, such that with the ultimate goal we want to extract work from this system as a result of the heat energy that is being utilized by that system, and then exhaust heat energy away. Obviously that's important because the basis behind heat engines, internal combustions, or even external combustion engines is the concept that we want to take heat energy from a source and do work with that, and be most efficient that we possibly can in the process of going through this thermodynamic process. So let's begin today with the idea of temperature and heat, and looking at the study of temperature changes and the relationship to heat exchange in thermal systems. The first thing we need to agree on or understand is the foundations relating to temperature. This is not unlike what we did in mechanics, where we first began by defining what we meant by the concepts of length, mass, and time. And those form the basis upon which we made measurements in our mechanical universe. So we're going to add to that list essentially now a quantity relating to the temperature of a substance. And we have temperature scales, 3 primary temperature scales that have been devised over the years based on different attributes, and they're all related, obviously. The oldest of those scales is the Fahrenheit scale, and it suffices to use water as the substance for which we will define the temperature scales, because water freezes and boils at a certain point with any temperature scale, and so we might as well use that as our way of defining that. So as you know, water freezes in the Fahrenheit scale at 32 degrees Fahrenheit. So that serves a benchmark for us to measure other things relative to that. And also it boils at 212 degrees Fahrenheit. The temperature scale Fahrenheit was originally devised on the basis of the temperature of human blood and thought to be approximately 100 degrees. As we know, it's not quite that, but nevertheless, it is a scale that is based upon our human physiology, and as such wouldn't necessarily have a certain universality to it that we would like it to have. Water is known to be somewhat a ubiquitous substance throughout the universe, and so we want to be able to define a scale of temperature just as we did mass, length, and time that's going to be based upon universal concepts. Remember that the concept of the meter was based upon the speed of light, which is a universal concept. Well, if we can base our temperature scales on a substance that we know would be universally found throughout the universe, or at least in the galaxy, then we have a means of communicating how we measure temperature. And as such, the Fahrenheit scale, based upon human physiology, is not the best way to do that. So we're going to base this. We're going to set up a scale. We're going to study a scale that is related to the boiling and freezing of water, where we use 0 for freezing and 100 for boiling. And that, of course, is the Celsius scale. The Celsius scale uses a logical two endpoints, 0 being the freezing point of water, and the boiling point of water being 100. The Fahrenheit scale, of course, uses 32 as freezing and 212 as boiling. So you can see, if you think about the difference there, the difference between 32 and 212 is 180 units on the Fahrenheit scale. Okay, 180 units. On the Celsius scale, the difference between freezing and boiling is 100 units. So the Celsius scale, actually, 1 unit of that is actually equivalent to 1.8 units on the Fahrenheit scale. That 1 over 1.8 is actually 5 over 9, a number that we will see later in our conversion formulas. So you might want to write these two numbers down presently. Where does water freeze and boil on the Fahrenheit scale? That's 32 and 212. And on the Celsius scale, that's 0 and 100. Now the Kelvin scale was devised later based on observations that were made with respect to the properties of ideal gases and the study of ideal gases that preceded the work in thermodynamics. And these studies led people to understand that as they were manipulating gases, their temperature, their pressure, and so forth, they observed a certain linear relationship between pressure or volume and temperature, as shown in this particular graph. Now, what we're idealizing here is that in the upper figure we see a piston, which is the darker shaded blue, and then a cylinder into which the piston fits in airtight fashion. The piston is movable in that cylinder, and inside the cylinder we have a gas, shaded material inside the cylinder. And so we can push the piston in, pull the piston out. We can add heat to it, we can make the gas expand, or take heat away and make the gas contract, and so forth. We can do lots of things to this ideal system. And as you can see by the graph, what we're actually demonstrating here is if we lower the temperature of the gas inside the cylinder, we observe that the volume will decrease linearly proportional to that temperature drop, as shown by the 3 data points. And we can connect those by a line and extrapolate that line back down to the 0 volume axis, and that will intercept the temperature axis at a certain point. If we are doing this measurement in the Celsius temperature scale, then we will find that we'll have our 0 degree mark here, and then we'll find that the volume is projected to go to 0 at some point below that. You can say, well, that's interesting. Perhaps we're doing this with one of our ideal gases, such as helium or neon. Okay. Now, if we replace that gas inside the cylinder with another gas and repeat the experiment, we find we still get a linear relationship between the volume, or in this case, we're plotting pressure and temperature. And that linear relationship, once again, shows that the line that we get for the data extrapolates to some point below the 0 Celsius degree point on the axis. So, for instance, if this data were collected from one ideal gas, such as helium, and this data from neon, the next ideal gas, and this data from argon, and we find that all three of these lines extrapolate to a common point, then we could say, wouldn't it make sense to define that common point as the 0 point of temperature on a scale that we're going to call Kelvin, in honor of Lord Kelvin, and then everything is measured above that, above 0. And in fact, we find out that the 0 Celsius point is actually 273.15 Kelvin units above 0. And so we have a temperature scale here in which there is no negative numbers, only positive numbers, and there's an absolute 0. There's nothing negative. Absolute 0 in Kelvin is, in fact, the 0 temperature, and nothing is below that. To date, the lowest temperatures achieved in the laboratory are on the order of 10 to the minus 9 Kelvin, meaning that you have 0 point and then 8 zeros and 1 as your lowest temperature yet achieved in a laboratory. Now that's not 0 because that's still a positive number, but it's certainly getting very, very close. Of course, you can imagine you can't actually get to 0. You can just simply try to keep making that number smaller and smaller. And the reason for doing that is there's some interesting physical phenomena that occur at the extremes of temperature and energy and velocity and so forth. And it's interesting to study behavior at these extremes. We find out some things that can be useful to us technologically in our everyday lives, such as superconducting materials. So the Kelvin scale has been devised actually from fundamental principles based on the fact that the pressure, temperature, and volume relationship for an ideal gas all extrapolates to one temperature, which we define as 0 Kelvin. And that's what is being referred to here, is that as we look at the data, these different gases, whether we're measuring pressure versus temperature or volume versus temperature, these different gases will extrapolate to that point on the axis down here, which we have now identified. Instead of being on the Celsius scale, it would be minus 273.15. On the Kelvin scale, we'll just call it 0, and everything is scaled up from there. So 0 Kelvin, 273.15. There's a few more digits, so sometimes it's rounded off to 273.16. For our purposes, we will just focus on using the 273 as our number. So when we're converting between Celsius and Kelvin, a Celsius reading of 0, where water freezes, actually will be a plus 273 Kelvin reading. So here's a table that shows the relationship between the three temperature scales. We have the absolute 0, and notice that absolute 0, which is 0 Kelvin, corresponds to negative 273 degrees Celsius. Notice I've dropped the decimal amounts there. And that also corresponds to approximately minus 460 in the Fahrenheit temperature range. Now, as you move up to the point where water freezes, you'll notice the Kelvin scale goes 273 steps up from 0 to 273. The Celsius scale goes 273 steps up from minus 273 to 0. So in fact, the Celsius and Kelvin scales have the same size unit. They just simply have different starting points. The 0 of Celsius is actually at the 273 mark of the Kelvin scale. But notice that in the Fahrenheit scale, going from 0, absolute 0 on the Kelvin to where water freezes, we're going from minus 460 to plus 32, or roughly a change of 492 units. So it's not quite as convenient to use that scale because the units don't have nice even increments like we have in Celsius, 0 to 100 or 100 units between freezing and boiling of water. And finally, you'll notice that where water boils, it's 0 to 100 on the Celsius scale. That's also 100 units on the Kelvin scale, from 273 to 373. However, on the Fahrenheit scale, as we said before, it's from 32 to 212, or 180 units. But given this information based on these benchmark values, we can write relationships which show how to convert between these two scales. And you may have to do this on some of your problems, your homework problems. If the information is given in one temperature scale and you need to convert it to another one. So these are handy formulas to have available for you. And these are on formula sheets in the back of your book as well. So notice in the Celsius, if you want to know the temperature in Celsius and you know it in Fahrenheit, you subtract 32 from it and then multiply by that 5/9. Now we know where that 5/9 comes from because that's the ratio of 100 over 180. And that's because the same physical change going from a freezing to a boiling of water takes 100 units in the Celsius and 180 units in the Fahrenheit scale. You can turn that formula around and you get a formula showing the conversion from Celsius to Fahrenheit by multiplying the Celsius by 9/5, which is the inverse of 5/9, adding 32, and then you have the Fahrenheit reading. And of course, the Celsius to Kelvin reading is just simply a shift because Celsius and Kelvin are the same size degree. They're just simply that the Kelvin starts at 0, whereas the Celsius would be starting at negative 273 at that same point. And those are the temperature scales we're going to use. For the most part, we'll stick with the Kelvin scale. Sometimes it's okay to use the Celsius scale if we're talking about changes in temperature. But if you're talking about utilizing a temperature in a relationship, relationships like we will be doing with the ideal gas law and thermodynamics, you should just stick with always converting numbers into Kelvin and then using them in their formulas. We won't be using the Fahrenheit scale in any of our calculations. Now, a thermometer, of course, we just finished talking about measuring temperature and the temperature scales that go with that. So, the concept of a thermometer is just simply any device that registers some change as a result of temperature differences. And, of course, as you know, with typical glass thermometers where they're filled with mercury or alcohol, colored alcohol, you simply have a thermal expansion going on. In that case, where the liquid expands when the temperature changes. Of course, the glass expands as well, and that means that there's some air involved as a result of the glass expanding to a small degree along with the liquid. Other physical properties that change when temperature changes occur are resistance of carbon. Some color changes can be involved. Some electrical properties can change, and so anything that changes in the context of a temperature change can be used as a means of determining temperature. Oftentimes you have to have a calibration or a standard to first establish where that 0 point is. For instance, with the thermometer, you can imagine that the liquid placed inside the thermometer and the glass tube sealed up, and then you would have to say put it in an ice bath at 32 degrees or 0 degrees Celsius, and then mark on the thermometer that point where where the level is, and call that 0 Celsius, and then put it in a steam environment where it's 100 degrees Celsius, and then mark that point on the glass tube, and then mark off 100 increments in between those two, and there you have your thermometer. But you had to calibrate it to begin with.